Quindi voglio parlare un po'.
Now I'd like to talk about numbers. Here you could see numbers. And what is a number? Well, my personal story with this book is a long story. At least 10 years ago, I had a contact with a publishing house, and they asked me to write a book on numbers, and I thought, how easy. So I wrote first half, second half, then the end, but it didn't work really. I wasn't happy about it, so I left it, and a year later I started again, another idea, another chapter, wasn't happy. In the end, I asked myself this question: what is a number? And I was unable to give an answer. Why? Well, it's clear, it depends. It depends on many things. It depends if we want to count. For example, use one type of number, right? If we want to compute and specifically divide, if we want to calculate roots, if we want to solve equations, and so on. So the answer to what is a number, in fact, has many answers. And I would now like to talk about some of the answers to that question. These are journeys through maths. There are 4 journeys here. The first question is, when did humans start to count? We don't know. We don't know, and we can't know, because this is a long, long, long time ago. Some say that numbers were created to count animals, 4, 5, 6. But others say that calendars were the reason. People started observing days, years, months. And you know that these numbers, that is to say, the numbers of days in a week or month, they're strange numbers. There's not a good relationship amongst them. So you need maths to be able to order this disorder. I think that by counting, human beings understood what time is. You could say yesterday, tomorrow, and so on. This is the oldest counting number of the world. It's a bone, it's of a wolf that is 30,000 years old, and you can see that there are many lines, and these are numbers. This is the first evidence, 30,000 years ago. Was one of the first cultural artifacts of humans. We don't know why this person wrote those numbers, but we do know that somebody did it, because it's a lot of work to do in a bone, dangerous, but it was done. And we have this that now bears witness of it. These are large numbers. We may think, but we're not sure of what it was. Nobody knows. Then, if we observe numbers in this abstract way, we see that the theory of numbers goes from the past to today. There's another bone, which is Ishango's bone, and there are some prime numbers, and mathematicians, ever since Pythagoras, about 2,500 years ago, to date, have tried to understand the properties of numbers, and understanding for mathematicians means that you prove it. So they have written theorems, and, for example, there is an infinite number of prime numbers. The Greeks understood this 2,000 years ago on a classification of Pythagorean triples. A question, how did they calculate these things? How did the Romans multiply? How did others multiply? If you want to build a Colosseum, you must calculate things. We don't know exactly how they did it. This is the Egyptians' system. The example is 27 by 23. The first, let's consider 27, and so the left column. The first step is that we divided 27 by 2, 13.5, but we're generous and we will not include the point. We take 13. And so on. 13 times 2 is 46. So this is the left column. Now the right column is always the double, so 13 becomes 46, 92, 184, 368. Then we still have to go back to the left, and we see the odd numbers. Odd. They're in bold. For every odd number, we consider the number to the right. So 13, 46, 3, and 1. We sum these numbers, add them up, and this is the result. It's a rather complicated method. Yeah, very complicated, but there are only two operations. Dividing by 2 and then doubling, and this can be done with an abacus and other such tools. So it's only slow. It's not complicated, but quite slow, because it requires many yes, and you have to learn the operation, then you can do it. Very probably they didn't know why it worked. I've put the expansion in brackets. In fact, it's a hidden binary system, but they didn't know. The Egyptians didn't know. Nor did the Romans. But it's one of the many possible methods to calculate before we had a decimal system. I would like to now explain a method of modern mathematics, which is an application. You need 2 slides to prepare for it, but it's interesting. Let us observe we have the powers, 2 to the power of 5, that's 32, and the 2 is important. We start with 2, and that's 2. And 2 to the power of 9, or 2 to the power of 13. 3 to the power of 5 is 243. The 3 is important, and so on. This is a theorem by Euler. In the very specific case, any natural number m and its powers, special powers, 5, 9 to the power of 5, to the power of 9, to the power of 13, 21, have the same digit in the unit's place. It's a miracle. No, it isn't. It's a theorem. But there's a virtually magical trick there. And I asked myself, what is the 13th root of this number, which is an enormous number, 96,889,010,407. We're looking for r, a natural number, so that r to the power of 13 corresponds to that number. And Euler's theorem says that r and r to the power of 13 have the same digit in the unit's place. Therefore, it's the 7 units, so r must be 7, or 17, or 27. That's a small calculation. That means that it can't be greater than 10. This is a special case. This is the most complicated of all the slides I'm showing you at the conference, but I will be explaining it. Here you can see this formula. This means that we take m, a natural m, and we calculate an odd power, strange number. This will be a very, very, very big number. And mod n means we divide it by n and we only consider what remains. So we're not interested in the order of magnitude or the result, but only in what is left over. And it's m in the end, the m we started with. This is a well-known theorem by Euler, and in 1976, 40 years ago, a group of mathematicians, young mathematicians, sort of new methods to encrypt and decrypt, and one of them looked at this theorem and thought that m maybe is not a number, maybe it could be a message as in number. And in this message, the formula says we could do something very complicated and we get m as a result. And he thought if we could divide this process, which is very complicated, in 2 parts, and we call the first part encrypting and the second part decrypting, then we have a crypting system, because m, which is then decrypted, gives m. This is a very simple idea, and they worked it out. This is called an RSA algorithm, and it's one of the well-known algorithms of encrypting, which is used in the internet, in mobile phones. And here you see the operations here. There's the public key, and the receiver has to calculate c to the power of d and receives the message. End of part 1. Peano. Giuseppe Peano, the famous mathematician, is well known for many things, but in all the world, he is famous in particular for natural numbers. Peano wrote a very formal, very high-level theory, but in fact, the idea of counting, you see, the first axiom says 1 is natural, which means that we must start at some point. The third axiom says if we arrive at a number, we can also take a further step forward. There's always a plus 1. And the fourth axiom says in this going on, we never have a cycle. We always go on. This is a theorem, a very complicated one. This is the first journey for maths. Secondly, another point. Writing number. These Greek mathematicians never wrote real numbers. They always wrote n. And the first numbers, as you saw in the bone, are a number of stripes. We don't know what they stood for. The idea that many people have thought of over the world is, let us put some small units together and let us create a higher level unit. I can imagine that the calendar was one of the ideas, because a month is clear. A month is roughly 30 days, and a year has roughly 12 months, so we can calculate how many days there are a year. But the first system of numbers was invented about 4,000 years ago in Mesopotamia. They did not use a decimal system, but a system in base 60. This is something that we use today, because 1 hour has 60 minutes and 1 minute has 60 seconds. This has been going on for 4,000 years. They also wrote figures from 1 to 59 with these two symbols, 1 and 10, and then they used, as we do, units of 10, but in Mesopotamia it was 1 and then 60, and not 100, but 60 by 60, 3,600, and so on. This was a system which was perfect. They were able to calculate very well, but they did not use 0. 0 is a very special number. For many centuries, there was no 0, because human beings thought that if there is nothing, we can't write something. We could also say nothing. It's not true. The first 0 in history was invented by the Maya in South America, but our 0 comes from India. It was invented more than 1,000 years ago. We don't know how. This is the first document, but clearly they had been using it for a while. And the Arabs brought the 0 to all the world and to Europe. It was 1202 when it arrived in Europe, and this brings us to Fibonacci, one of the great mathematicians of the Middle Ages, Leonardo Pisano, who wrote a book, a very interesting book, because he doesn't start with thank you or motivation or application. He starts with a theorem. The theorem is the 9 Indian figures are 9, 8, 7, 6, 5, 4, 3, 2, 1. With these 9 figures and with the sign 0, which the Arabs call zephyr, any number whatsoever can be written. This is a perfect symbol, and all the rest of the book are exercises which show the advantages of the new system. Any number can be written. Some very large numbers, which the Romans were unable to describe. 100,000 are the number of heartbeats in a day. 1 million. It's the life salary of a life. 10 million inhabitants in the largest cities of the world, 100 million, the population of Italy, France, Germany, 10 billion world population, 1 trillion, the debts of a typical European country. And then we have the natural constants, and physicists too have calculated the number of atoms in the universe, 10 to the power of 78. And this is the largest number in our universe, in reality, real number. But in maths, we use much larger numbers, 10 to the power of 200 numbers, which we use in the RSA algorithm. Your mobile phone can use these. And then the largest prime number to be known is 10 to the power of 22,338,618. It's not enough. You can't divide it by 2, by 3, for 5. It's never ending. What are the advantages of the Indian system, the decimal system, which is now used in the whole world? This is by a quote by Menninger, who's a German mathematician. He says there are few things on earth that are perfect, and the perfect customs which man has successfully created are fewer still. But he can pride himself on this. These new Indian numerals are indeed perfect. Fine. One can write numbers of any order of magnitude. It's easy to compute. I think that this has been the essential advantage, because henceforth everyone was able to calculate, not only mathematicians, anybody. And the idea was that we calculate, we can to reduce, then to calculate with figures. You all know that if we multiply two numbers, large ones too, it's enough to have a table and you can check results. Now, third point 3, very quickly. Very soon, human beings noticed that natural numbers were not enough, because we have to measure with more accuracy. There's always a distance between 1 and 2, 2 and 3, and so on. Sometimes you need intermediate values. And if we want to calculate with greater freedom, in particular to divide without limitations. In antiquity, they only had natural numbers, integers. A fraction such as 2/3 was not considered a number. Bernard Bolzano was a very interesting mathematician, also in terms of numbers. He said we cannot give an answer to the question, what is a number? Because it's a pointless question. What I can say is, what are numbers rather than a number? He says numbers must always be had in the plural. It's a number of things, it's a set of things which I can use to calculate. For instance, rational numbers are numbers. We can fractions, sums, and differences. Real numbers are numbers that can be used to calculate it. So it's a very interesting point of view. Numbers are always plural. But let us start with the last part, which in turn is divided into two, that is to say, irrational numbers. Pythagoras. The Pythagoreans were convinced that all is a number, and precisely that each number is the key to the numbers are the key to the universe, because the world consists of numbers. More specifically, they say that each magnitude is either a natural number or a relationship of natural numbers. And I think that the convincing example is music. They measured, for instance, the length of the strings or chords, and they noticed that the ratio corresponds with the musical interval. 2 to 1 and so on. But they also had they represented this in a geometrical figure, which was the pentagon or pentagram, and they noticed that not everything is a number. There are some numbers that are completely different from others. And if we observe the horizontal diagonal, this has a long part from left to the red dot, which we call M, capital M, and we call the other section small case m. And the Pythagoreans asked themselves, what is the relationship between these two, the ratio? We could say 2 to 1. It's nearly true, but it's not completely true. 3 to 2, better, but not. 5 over 3, more or less. But we can approximate it increasingly better, but you never get to it. This ratio is never a fraction of two natural numbers. So this is an irrational number. It's the first irrational number that human beings have come across. And they calculated this, they proved it with a mathematical and very intelligent manner. But the most famous irrational number is the square root of 2. We should imagine a square with the side which is 1, and then the diagonal is square root of 2. And it was discovered more than 2,000 years ago, and Euclid proved the fact that this number cannot be a fraction of two natural number or a quotient of natural numbers. This was proved 2,000 years ago, and I would like to show you a demonstration which is very beautiful, which is quite recent. This is a demonstration by Tennenbaum in 1950. He was an American student, and this was his only contribution to mathematics, but it's very beautiful. He develops his thoughts as follows. Let us assume that the square root of 2 is a rational number. And then we will reach a contradiction. If it is rational, then there exist natural numbers a and b, whereby the square root of 2 is a over b. It follows that 2 equals a squared over b squared, or that a squared equals 2b squared, and thus a squared is b squared plus b squared. We can have a geometrical interpretation. There is a square with a side A, so that its area is equal to the areas of 2 squares with side length b. Well, this is when it's translated into geometry. We take the smallest square, the smallest number. Let A be the smallest number with this property. And Tennenbaum drew this situation. Here you can see a large square with an A length squared and 2 small ones, the green ones, which have B as a side. And the formula says that the 2 small squares altogether are the equivalent of the square. This means that the intersection of these 2 squares is the same as the 2 white squares. Is this clear? But so the double, and we have reduced another square, which is the one in the middle, whose area is equivalent to the area of the 2 white squares. This is not possible. This is a contradiction. So the root of 2 is an irrational number. I think that it's a very beautiful demonstration, which has a small disadvantage. You can't generalize it. Root of 3, root of 4, or 5. If a root of 5 doesn't work. Irrational numbers are a giant universe. All the roots, pi, we heard about that. Euler's number. And Maurice Cantor, the mathematician, proved that nearly all numbers are irrational. It's difficult to prove, but you can do it from a point of view that nearly all are irrational. There are also numbers that are more complicated, and they're transcendent numbers such as pi or Euler's, and these are very difficult to find. Individual transcendent numbers, difficult to find.
Allora, il viaggio finale.
The final part of our journey. Let us now consider equations. For all mathematics, this has always been a very important theme.
4.000 anni fa gli egizi hanno risolto
4,000 years ago, the Egyptians had solved equations
ci sono
with a method that I like very much.
una grandezza, un numero,
There are exercises of this kind. There is a number, an unknown number, an x, and its quarter give 15. So a quantity together with its quarter give 15. What is the quantity? We write x plus, we write this, and it works.
gli egizi hanno
But it's not funny. The Egyptians
non
worked it
sappiamo
out
la
this way.
soluzione. Quindi
They said, we don't know the solution, so
numero qualsiasi.
let us take a fake solution, any number, for instance 4.
4 è il suo quarto,
And we calculate it with 4.
5,
4 and its quarter give 5.
il risultato deve essere 25. Quindi
5. But the result must be 15, not 5, so 3 times. So we must multiply the fake solution by 4
la soluzione 12
and obtain the solution by 3. Sorry.
un metodo molto
And
simpatico,
this is
molto ingenuo.
a very simple and very intelligent solution.
Abbiamo due
What does it mean to solve an equation? Here again, we have two very important answers. The first is there is a number
la equazione. Numero qualsiasi.
which
Qui è la risposta.
solves the equation, any number, whatever the number. In this case, the answer is a very strong yes. This is the fundamental theorem of algebra. Many mathematicians have proved it, including Gauss, who proved it 4 different times. You could also have complex numbers, but this is a technical aspect. Second question is more interesting, and is there a formula such that one computes the solutions exactly, so that when we put the coefficients of the equation, you have solutions? Here you see famous mathematicians who tried and gave a contribution. Then we have quadratic equations. They're easy. We did them at school. Mathematicians did them for centuries. A very important mathematician is Vieta, who was the first one to formalize these. Everybody did this, but cubic equations were not solved in antiquity, and Scipio del Ferro found a formula, but he said he did, and he only gave it to his student, so no one heard about it, only maybe the student, Antonio Maria Fior. Then we have Tartaglia, who was a mathematician who was very good. He had a life which was not so good. He was a good mathematician, and he said, I can solve cubic equations. And Fior, who was Scipio del Ferro's student, didn't believe him, because only his master, he said, had been able to solve this. And they had a challenge. And Tartaglia and Fior contributed with many cubic equations. Each one exchanged it with the other, and the other one had to solve it. And Tartaglia solved all the equations, Fior none. So clearly Tartaglia had the solution. The formula is here. It's a little complicated. Plus, minus, squares, roots, cubic roots, so on. But it's a formula.
Osservazione è interessante che Tartaglia ha potuto provare che lui ha
An observation is interesting that Tartaglia could prove that he had the knowledge without revealing his secret. No one knew what his secret was. That's cubic, and now we go on to fourth degree. The formulas become a little bit more complicated. Then fifth degree, more complicated. That's what mathematicians thought, but that is not actually so. For fourth degree equations, that's true. It's a complicated formula. But with equations of fifth degree, stop. In equations of fifth degree, sixth, seventh, etc., there are no four general formulas. This is a theorem, so it is true. It's the Ruffini after Abel that proved this rigorously. And this was a shock, because it means that the mathematical means have limits. Not the mathematical tools, they have limits, but this theorem does not say that we haven't found a formula, but maybe an extraterrestrial could find a formula. No, 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 the theorem says something else. It says we haven't found a formula because there is no formula. But mathematicians have answered this challenge and have tried to understand why. And they've developed a theory, which is Galois theory, with the Galois extensions, Galois groups to understand. It's a very beautiful theory, but a little advanced for this occasion. But believe me, it's a very beautiful theory. So let us go back to the beginning, summarizing what is a number, what are numbers. As I said, there are many answers. If we want to count, it's enough to have natural numbers, 1, 2, 3, 4, etc., etc. If we want to write numbers, large numbers, we need a positional number, for example, decimal numbers. If we want to measure and compute, divide, and so on, we need rational numbers. If we want to solve equations, roots, algebraic numbers, and transcendent numbers, and pi, we need all of this. I hope I've been able to convey some of the fascination which I have for number. I would like to thank you very much for your attention.